Hello, it's Dr. Gibson. Welcome to our video for Module 4. This is analysis of variance, typically called ANOVA. All right, so our highlights here this time, if you will, our main points. Why would we use ANOVA instead of t-tests? They're pretty similar. When to use ANOVA. What is a one-way ANOVA? This is the particular type of ANOVA that we're going to be doing this week. ANOVA in general, and then looking back to independent t-test results. So, why use an ANOVA instead of t-tests? The main reason is that if we do multiple t-tests, the probability of an error due to randomness compounds. For example, an ANOVA that is comparing three groups at a 0.05 level significance will get a 0.05 probability of wrongly rejecting the null due to random error. If, on the other hand, you use three t-tests, each at the 0.05 level of significance, the way the probability works is you take 1 minus and then 0.95 to the third power. You get a 0.143 probability of the same error, wrongly rejecting the null hypothesis, right, due to random error. So I think the reason using ANOVA is pretty clear. Use the ANOVA 0.05% probability of getting the random error. Use three t-tests, 0.143. The more t-tests you have to use, the worse it gets. All right. So that's why we use an ANOVA instead of multiple t-tests. When to use ANOVA? So ANOVA is used to test for significant differences among means of three or more groups for the reason we just talked about in the last slide. All right. Then if the ANOVA, the analysis of variance, demonstrates that there is a significant difference somewhere in the groups, then a different test called an ad hoc test is run to determine the details of the difference or differences. The ANOVA itself only tests for the presence of at least one significant difference somewhere between all of the means. All right, the means of all the groups, okay? Now, so what is a one-way ANOVA? One-way ANOVA is used when testing the effect of one independent variable on three or more groups. So an example of one-way ANOVA is this. You're going to compare the results of three different weight loss plans. In this case, the independent variable is categorical or nominal, where values of the variable are names of the three different plans. All right. All we're going to do in the one way is test the difference in the mean weight loss for each of the three plans. Now, for a two-way, we're going to extend this exact same study to another variable. Extend the example above to include another variable such as gender. This ANOVA would test for differences in mean weight loss study by both type of plan as well as gender. See, there's two different variables that'd be a two-way ANOVA. It would also test to see if there's an interaction effect between the type of plan and gender. All right, so you get changes by plan, changes by gender, and then maybe a different set of changes where gender and plan interact. This two-way ANOVA could check for all of that. All right, and ANOVA can be extended to more than two independent variables. You can do a three-way, a four-way. It's just that the more variables you're trying to check for, the more data you need. All right, so looking back at our independent t-test results. So first in the group statistics table. So here's the report. This is our example report, okay? So let's go down to the group statistics table. So here's our group statistics table, right? In the group statistics table, the average standard error of the mean is about 0.6, and the difference between the means is 2.3, right? So if you remember, if you divide this, the difference between the means by the 0.6, you do get a number that's greater than 2. In fact, it's almost 4. So the eyeball test definitely predicts there will be a significant difference between these means, and in fact, there was one. All right. Now, I'll look at another facet here of, let's look down at the independent samples t-test table, look here in the middle where we're talking about, the 95% on the edge here, 95% confidence interval. So you'll see this in some tables. What it means is so a 95% confidence interval of the difference. So what this is saying is the test is telling us that there's a 95% chance based on the sample data that the actual difference between the means, in other words, the difference between the means of the populations, not the samples, is somewhere between, right? If you assume the variances are equal, which is what we did based on one of our assumptions, it's somewhere between minus 4.110 and minus 0.524. Okay. In other words, the difference is negative. And there's a bit of a range there, even to be 95% sure, right? A 95% range is in that, between those two numbers. That's what a 95% confidence interval. All right. So now it's time, right? We've got our usual study, some practice, and then you're going to get the chance to perform a one-way ANOVA. All right. It's Dr. Gibson. I'll see you next week.